Afternoon, everyone, again. Okay, so last time we introduced the idea of a sequence. Well, we spent a while introducing the idea of convergence as a general concept and explaining why it was important in maths or science, mainly emphasizing places, or why convergence is important as an idea that lies behind most of mathematics modeling and the way you model the real world and obtain solutions to these models. Okay, so then dealing with the material that's in the notes, getting to grips with the actual material we're working through in the lectures, we started off with the definition of a sequence. Okay, so just very brief run through what we did last time. The definition of a sequence is simply an ordered list of numbers, or more generally other types of mathematical object functions and so on. And we introduced this kind of notation that you see here in definition 1.1 and being used in the examples after it, of naming a sequence with a particular letter and using subscripts on the letter then to denote the particular elements of the sequence. So x1 is the first element, x2 is the second, and so on. Okay. We talked through a few of these examples last time, just talking about a few interesting sequences, the Fibonacci sequence, the prime number sequence, and so on. And then we introduced a bit of a classification of certain kinds of sequences, so certain kinds of sequences that exhibit very regular pattern. These were arithmetic sequences and geometric sequences. Arithmetic sequences were the ones that always, each sequent element was a fixed, you get from one element to the next one by adding some fixed number associated with the sequence. So a general one would look like some initial term A, then A plus D, A plus 2D, A plus 3D, and so on. So there's a fixed difference between subsequent elements. The geometric series, on the other hand, where there was still a regular pattern, but this time it was a fixed multiple, not a fixed difference between elements, but a fixed multiple. So the first element might be A, and the second one A times R, the third one A times R squared, and so on. And we maybe looked at some examples of those, and we highlighted the important example of geometric series, which is one that you use, it's the so-called compound interest formula. So the basic formula that tracks, say, the value of some initial investment according to a regular compounded interest rate. That'd be the good one. I suppose the less good way to look at it is it tracks how the size of a debt grows. If you have some initial debt and it's just left to accumulate interest in a compound way, then this formula tells you how the debt will grow over time. Now, we're looking at sequences because sequences are the first place where we're going to study convergence. We're going to look at these infinite sequences and develop the theory about how some sequences might converge to a limiting value and others won't. Okay. But before we get on to the exact definition of convergence, we're just going to look at just a simpler study of sequences, and that is describing the way that some sequences might be increasing sequences and others might be decreasing. Okay, so definition 1.3, which you have in your notes and is just reproduced here on the screen, it's quite straightforward. Just introducing these terms, an increasing sequence and a decreasing sequence. So an increasing sequence is one where, well, it's a sequence, let's say it's called xn, and it's one where x1 is always smaller than x2, and x2 is always smaller than x3, and so on. If the sequence satisfies those inequalities, it will be called an increasing sequence. And similar thing for a decreasing sequence. If x1 is always bigger than x2, and x2 in turn is always bigger than x3, and so on. Okay. And so this is at the bottom of page 3, that definition there. Now, at the top of page 4, we have this idea of being able to prove increasing or decreasing behavior. So if we have some formula, algebraic type formula for the sequence elements, how might we approach proving that the sequence is either an increasing sequence or a decreasing sequence? Well, there's at least two ways to approach it. You can either look at, so this first bullet point here, either look at the difference between consecutive terms. So you can analyze the general term an plus 1 minus an. So here we're talking about a sequence of terms called a1, a2, a3, and so on. So you consider the difference between subsequent terms. So an plus 1 is some term in the sequence, and an is the one that comes just before it. And you'd examine this difference, and what you'd be trying to do would be to compare it to 0. Now, why would you be comparing it to 0? Well, you'd be comparing it to 0 because if you show that an plus 1 minus an is bigger than or equal to 0, of course, that's equivalent to, this is equivalent to saying that an plus 1 is greater than or equal to an, i.e. that's an increasing sequence. Similarly, if you show that the difference an plus 1 minus an is less than or equal to 0, that's equivalent to showing an plus 1 is less than or equal to an, i.e. that's a decreasing sequence, a sequence where the terms are getting smaller and smaller. So that's one way to do it. Look at the difference and compare the difference to 0. An alternative approach will be not to look at the difference, but to look at the ratio of consecutive terms in the sequence. So to look at the sequence element an plus 1 divided by an. Now, when you're looking at the ratio, you don't compare it to 0, you compare it to 1. Because how the ratio compares to 1 tells you how the top and bottom parts of the ratio compare to each other. So if you can show that an plus 1 divided by an is bigger than or equal to 1, that's, again, equivalent to showing that an plus 1 is greater than or equal to an, i.e. An increasing sequence. And if the ratio an plus 1 is less than or equal to 1, that's equivalent to the sequence being a decreasing one. Okay, so let's see if we can apply this to an example. So we'll have a look at this particular sequence an here. It's this example 1.6. I think it's worked out there on page 4, but we'll just go through the calculation and go through the analysis of it. So this sequence an has a nice formula for the nth term. It's 5 to the power n divided by n factorial. Now, just remind you what n factorial is. So this n followed by an exclamation mark represents the factorial of the integer n. And the factorial of n is defined as this big long product here. So it's the definition for the factorial of a positive integer. It's n multiplied by n minus 1, multiplied by n minus 2, etc., multiplied by all the integers all the way down to 1. Or I guess you could leave off 1 because that doesn't affect its value. But so it's just the product of all the integers from n, all the positive integers from n down. Now, it's not immediately obvious when we look at the sequence definition whether it's increasing or decreasing. It doesn't leap off the page at you necessarily. Except to say that, well, because the thing in the top is an exponential, 5 raised to the power n, well, I was going to say that exponentials increase, but of course factorials also increase quite fast as well. So the top is increasing fast, it's an exponential, you're multiplying by 5 all the time. The bottom is a factorial, that's increasing fast. So both the top and bottom are increasing. So again, it's not clear overall whether the ratio is going to be increasing or decreasing. However, you might start to think that, well, the factorials, you're going to be multiplying by large integers each time. So actually, after a while, the factorial is going to be increasing faster, which will probably start to drag an down, because the bit that's increasing fastest is in the denominator. So as the denominator grows a lot, the fraction is going to start to get quite small. So maybe we'd expect this sequence to ultimately be a decreasing sequence. Now, of course, one way to investigate that would be just to start calculating terms in the sequence. So here's a little evaluation window. It's actually part of a software package called Sage. There's a link from the presentation to the Sage website where you can investigate it a bit. But it's just another mathematical package like MATLAB, which you've been introduced to. But this is a little evaluation window. So what have I got here? Well, I've got the formula for the sequence, 5 to the n divided by factorial n. And there's this kind of construction here for n in the range 5. Range 5 stands for all the integers 1, 2, 3, 4. All the integers beginning at 1 up to the maximum of 5. And I'm going to do a list plot of those numbers. So this will give me, oops, go back to see it. This will give me a plot, which is this plot here. And the dots are, this dot here on here is A1, this is A2, this is A3, A4, A5, and so on. They seem to be increasing. But maybe that's just happening near the start. If I increase the amount of elements I'm considering, look at the first 50 instead, well, then you see kind of a clearer pattern of behavior, that the sequence kind of increases for the first few terms, maybe around the 4th or the 5th term, and then it starts to decrease very quickly, and indeed the terms shrink down very low very quickly. Okay, so that kind of tells us what to expect. But let's see if we can prove that in a systematic way. Because that investigation is all very well and it takes us up to the 50th term, but, you know, strictly speaking, who's to say what happens after the 50th term? Maybe the sequence starts increasing again after the 50th term. So to be 100% certain about it, we maybe want a more rigorous approach, or an argument that doesn't depend on just looking at specific values. Okay, so we'll take our term n, our definition for the nth term. So we're considering this sequence an, which is 5 to the power n over n factorial. And yeah, we'll have a look at it. So we might try, now when you're looking at sequences that have exponentials and factorials in them, very often it's good to try the ratio approach. Actually, the two approaches are equivalent to one another. I mean, anything that you can show with the ratio approach, you'll be able to show with the difference approach as well, and vice versa. But it's just a different way of approaching it. It's just a different way of approaching the algebra. So we'll try the ratio approach. We'll look at this term an plus 1 over a to the n. Or you could look at a to the n divided by a to the n plus 1. That doesn't matter. As long as you're looking at the ratio between consecutive terms, and you remember that when you're looking at the ratio, you're comparing it to 1. So what does this look like? Well, so we've got a big fraction here. On the top of it, we're putting an plus 1. So an plus 1 is 5 raised to the power n plus 1 over the factorial of n plus 1. Okay, that's what an plus 1 looks like. Remember, if an is this, then an plus 1 would be 5 to the power n plus 1 over n plus 1 factorial. Because remember, look, here's the sequence index. It appears here and here. So if you're going to look at the n plus 1th element, you have to replace everywhere in the formula where the index element appears, you have to replace that with whatever the new index is, which in our case it's n plus 1. So that's the an plus 1 at the top of the fraction, and on the bottom we put an, which is just 5 to the power n divided by n factorial. Now, that's kind of looking a bit ugly on the page at the moment, this one fraction divided by another one. And maybe a cleaner way to look at it is the first fraction, which is 5 to the n plus 1 over n plus 1 factorial, multiplied by the reciprocal of this fraction that's in the bottom. So that's the same as n factorial divided by 5 to the power n. Looks a bit untidy on the page, having a big tower of fractions. This product of fractions where you've taken the denominator fraction and turned it upside down, just looks a bit easier to handle. And of course, when you've got two symbolic fractions multiplied together like that, you can kind of slide the factors around, because really this is just a big product of all these things on the top of the line and the bottom of the line. So actually, it would make sense to put all the powers of 5 together and all the factorials together. So just reordering the factors, really. Of course, remember that we're trying to compare this to 1. So just keep this in mind, that you want to compare this to the quantity 1. And ultimately, we want to decide whether this is bigger than or smaller than 1. So we would like to start simplifying it quite a bit. Now, if you just look at the powers of 5, we can simplify those straight away. Right? So you've got 5 to the power n plus 1 divided by 5 to the n. So you've got a load of 5s on the top and a load of 5s on the bottom. So they'll all cancel with each other, except that there'll be one 5 left over on the top. So we'll be left with a factor of 5. Okay, all the other factors will cancel with each other. So you compare them off together, one by one from the top and one from the bottom. You'll be just left with 1 on the top on its own. These factorials, how will n factorial divided by n plus 1 factorial behave? Well, n factorial over n plus 1 factorial. Remember what the definition is. It's n by n minus 1 by n minus 2 all the way down. And what's the factorial of n plus 1, of course, is the similar thing, except it begins at n plus 1. So it's n plus 1 times n minus 1, etc., all the way down. Put this on both screens for the moment. Focus. How do I get? I'm just trying to switch the other thing to this. Can't seem to do it. Okay, well, this simplifies in quite a similar way, because the top and bottom are nearly the same. This n here will cancel with this n. This n minus 1 cancels with this n minus 1. The n minus 2 here will cancel with n minus 2 here. I haven't written it down, but it's there. Okay, so this actually simplifies to 1 over n plus 1. Okay, because each factor here will cancel with a factor. Each factor on top cancels with the factor on the bottom. And then there's just that one factor on the bottom left over. So this boils down to 5 divided by n plus 1. Okay, that's a good deal simpler than what we started off with, this kind of ugly tower of fractions here. Now we just got this fraction 5 over n plus 1. That's a lot easier to deal with. Now, what are we going to do with it? Remember, we wanted to compare it to 1. Yeah. And it's fairly easy to do that. 5 divided by something else, we want to compare that to 1. Well, we can do that. 5 divided by n plus 1. This is, at the beginning, the bottom is going to be smaller than the top. So this is going to be strictly bigger than 1 whenever this n plus 1 is strictly smaller than 5. So that's whenever n is strictly smaller than 4. Of course, when n is equal to 4, For n equals 4, it's going to be equal to 1. But then for every n bigger than 4, strictly bigger than 4, the bottom is going to be larger than the top. So that's going to make it less than 1. So if we want to do a multi-line equation or a multi-line statement about this quantity, quite often we just put the different conditions on the different lines and use one of these large curly brackets. It's a kind of common convention for when you're working with these things. So we're saying that this quantity here is greater than 1 under this condition for n strictly less than 4, equal to 1 for n equals 4, and then less than 1 when n is bigger than 4. But of course, this is an plus 1 over an. So, i.e., we're saying an plus 1 is greater than an for n less than 4. An plus 1 is equal to an for n equal to 4, and that an plus 1 is strictly less than an for n bigger than 4. So there you can clearly see now the increasing and decreasing nature of the sequence. It's increasing for a while early on. So A2 is bigger than A1, A3 is bigger than A2, A4 is bigger than A3, but then A5 is equal to A4, but then after that, A6 is less than A5, A7 is less than A6, A8 is less than A7, and so on, okay? So we can say this sequence, now when you do curly brackets an, when you write it like that, this means you're referring to the sequence as a whole. So you can say this sequence eventually, i.e. after n equals 4, you can say is a decreasing sequence. Increases for a few bits at the start, but then ultimately it's a decreasing sequence. Well, as I said, where we want to get to is talking about the convergent properties of sequences, but at least being able to talk about and look at how a sequence might always be increasing or always be decreasing, that's a kind of first basic look at the long term or the overall behavior of a sequence. But where this argument has something slightly more going for it than this numerical investigation that we did with the plotting of the first 50 points. Okay, the plotting of the first 50 points more or less told us what was going on, but it was ultimately only looking at the first 50 points. And so it's a bit of a logical leap to suddenly start concluding that, well, yeah, the whole sequence is always decreasing. Whereas this argument over here, it's just a little bit stronger because, you know, all the time we were talking in general about the general term an and, you know, reaching fairly clear conclusions talking about all of the sequence at once. Okay. Any questions about that or things that you'd like me to clarify about it? Any of the points you'd like me to explain again? Okay. Okie doke. So here's a few examples. Why don't you take a few minutes to have a go at these? Give yourself a break from listening to me. So we'll take at least 5 minutes, maybe a bit more. So you can start having a look at these. Do talk about it with your neighbors. Okay. So try doing I didn't illustrate the difference method, of course, there, but so you could try using the difference method or the ratio method on those. If you got any queries you want to shout out or any questions, please feel free to ask. No. So I said, strictly speaking, they're two equivalent approaches. Anything you can do with one, you can do with the other. It's just comes down to it's just the way you arrange the algebra. I kind of feel myself that if the thing involves exponentials or factorials, that might be easier to do with the ratio thing because they cancel factor by factor. But when you look at the difference, you can factorize expressions as well when you're looking at the difference. So it's more or less doing the same thing. So to take the difference approach to Sn plus 1 minus Sn. So be careful when you're writing down, writing down Sn is easy because it's kind of written already in the definition. It's 3n over 4n plus 1. That's what Sn is. But just be careful when you're writing down one of these relative terms. So Sn plus 1, you see the rule for Sn is 3 times the, a certain index position in the sequence S is 3 times the index divided by 4 times the index plus 1. So at the top here, we need to have 3 times the index, but you see the index is now n plus 1 here. And on the bottom, you have 4 times the index plus 1, so this is 4 times n plus 1 plus 1. That'd be what you would get down for the difference. Now we're going to have to do something with this, but ultimately we want to compare it to 0. Tell whether it's bigger or less than 0. At the moment, it's a difference between two things, so we have to know which one is bigger. But it's maybe not immediately obvious, because in this fraction, both the top and the bottom are both bigger than this, so it's not amazingly clear whether this is bigger than this or not. But one trick would be to, or one way to simplify it a bit, is to instead of looking at it as a difference between two quantities, a difference between two fractions, to look at it as a single fraction. So how do you take two symbolic fractions and write them as a single fraction? Well, you need to choose some common denominator, some denominator that you can transform both of the fractions easily to. And in the absence of anything else, you can always use the product of the two denominators. So you take the denominator from 1 and you multiply it by the denominator from the other one. And then the numerator is, that kind of cross product kind of thing. So you take 3 times n plus 1. That's multiplied by 4n plus 1. And then you subtract 3n times 4n plus 1 plus 1. Which brings us to that fraction there. Okay, that hasn't really simplified it really in terms of the amount of, it's probably more characters written down on the page. But it's kind of simplified because it's now just a single fraction. And a single fraction, it should perhaps be easier to decide whether it's positive or negative. Now, it'll be worth our while multiplying out the numerator here because we're adding and subtracting stuff. So hopefully maybe a lot of stuff will cancel out. Before we go and do that, just as an aside, if you have any fraction, x over y, how do you decide if that's bigger than or less than 0? How do you decide if a fraction is bigger than or less than 0? Well, it just depends on whether x is bigger or less than 0 or y is less than or bigger than 0. If they're both positive, then the fraction is positive. If they're both negative, well, then the fraction is still positive. Negative divided by negative is positive. Whereas if one is positive and one is negative, then the whole fraction is negative. So if I can tell separately whether the top and bottom are positive or negative, then I'll know what the whole fraction is. Now, is the bottom positive or negative? Positive, because it's just a load of positive stuff added together and multiplied. And the possible values for n are just n equals 1, n equals 2, so they're all positive, 3, and so on. So you can tell straight away that the bottom is positive. So it's just a load of positive stuff multiplied and added. But the top, it's not immediately obvious because there's subtractions involved. So it may be positive or it may be negative. But if you multiply out all of this, what do you get? Well, you're going to get a 12n squared, don't you? That's the n squared. How many n's are there? There's 3n and, no, hang on. I have a 3n here. and multiplied by that. And then here you have 3, is it 12n? So it's 15n there, isn't there? And then the constant term is a 3 by 1 is a 3. Whereas back here, we're subtracting all of this. And again, you have 12n squared. And then you've got 12n. Is that right? No, hang on. You've got sorry, minus 15, isn't it? Yeah. Plus 15. Yeah. Cool. Thank you. And then the last bit, what do we have? What's the constant term? Well, there is no constant term. That's all there is. It's just 12n squared plus 15n. Yeah. So, and then these two brackets here are the same as they were above. And then that does simplify. This just comes down to 3 over these two brackets here. I won't even bother multiplying them out and simplifying them. Because the point about them is that this is something positive. This bit is always positive. This bit is always positive. So now it's pretty clear what the fraction overall is, because it's just 3, which is positive, divided by something positive. So the whole thing is positive. So the whole thing is bigger than 0. Okay, that's good, but it's not this thing in particular we're interested in, it's what this is. And this is Sn plus 1 minus Sn. So we have that Sn plus 1 minus Sn is bigger than 0. So i.e., what we've just shown there is Sn plus 1 minus Sn is bigger than 0. So this tells me that Sn plus 1 is bigger than Sn. So this is that increasing or decreasing? Increasing sequence. Because the term Sn plus 1 is always bigger than the one that came before it, Sn. You could probably investigate that. What was it? 3 times n. 3 times n divided by so you can see when you type it in the graph that is increasing. Of course, it does look like it's converging. What do you think it's converging to? 1? Doesn't really look like it. Looks to be something around here. This is sorry, 3/4. Yeah. 0.75. That which is about here, where the mouse is there on the vertical axis. That seems to be where the dots are getting closer to. And of course, you can kind of begin to appreciate why it's converging to 3/4, and we'll be able to make this a lot more rigorous when we actually look at what the definition of convergence is and start talking about it in very great precision. But you can see 3 times something divided by 4 times something plus 1. Well, it kind of looks like 3/4, but 3/4. But you think about as n gets very large, when n becomes a large number, you're taking something quite large, 3n, divided by something fairly large as well, 4 times n. The fact you're adding a 1 on to the 4n becomes less and less significant as the n part gets larger. But by the time n is 3 million, you're dividing 3 million by 4 million. The fact you're actually dividing it by 4 million and 1 is neither here nor there, really, is it? It becomes quite ignorable as n gets larger and larger. And that kind of tells you that as n gets larger and larger, that Sn quantity is getting closer and closer to 3/4. Okay. Now, we'll be able to make that, okay, that's a little bit of a hand-wavy argument, but we'll be able to make that kind of talk very precise once we actually get into the theory of convergence itself. The n squared over 2 to the power n, well, I wonder what that did. Did anybody get a conclusion for that one? Yeah? Was it going to be increasing or decreasing? Yeah. Anyone else? Well, n squared over 2 to the n, I think it's probably going to be decreasing. Because when n gets very large, although n squared will be large, 2 to the power n is going to get, you're doubling each time. So like when n is 100, okay, you got 100 squared, which is 10,000, but you've got 2 to the power of 100. When you multiply 2 by itself 100 times, you get an astronomical number. So the bottom is getting huge much quicker than the top. So I think this should be decreasing. So we should hopefully see that in the plot. Yeah, but it does increase for a bit at the start, but then it zooms down and decreases as well. And I mean, is that readily seen? With the pen and paper approach, n squared over 2 to the power n. Because there's an exponentials here, I'll look at the ratio approach. So fn plus 1 divided by fn, that would be n plus 1 all squared divided by 2 to the n plus 1. And then I'd have to multiply that by 2 to the n over n squared to get the reciprocal. Because dividing by fn is the same as multiplying by 1 over fn. The 2's cancel, except they leave a factor of a half behind. You got n 2's in the top and n plus 1 2's in the bottom. Sorry. I'm just choosing to use this approach. You can use either approach. Either look at the difference between terms or look at the ratio between terms. I chose the ratio because there were exponentials here, and they cancel quite nicely when you have them one divided by the other one. But then I'm left with n plus 1 all squared divided by n squared. And what can we say about this? Well, this is a half times, actually that's the same as n plus 1 over n, all of it squared. Take the squaring kind of outside the fraction. Actually, maybe this one isn't so straightforward to analyze. I mean, you can also rewrite that fraction as 1 plus 1 over n squared. And so, yeah, you kind of have, remember, we're looking at the ratio, so we want to compare this to 1. Well, you kind of have to worry about the square root of 2. What's the square root of 2 is, what is it, 1.114 something. So as soon as you're beneath 1.41, isn't it? Yeah, sorry. Yeah, that's a bit low. 1.41 something. But as long as you were sure that we're beneath the square root of 2, which we would be when n is 4, 3, 5. So probably when n is past 3. So we could probably say for n strictly bigger than 3, this is less than a half times the square root of 2 squared. And so that ultimately this is less than 1. So i.e. decreasing. Fn plus 1 is less than Fn for n bigger than 3, so decreasing. Which is what we saw in the computer plot as well. Yeah, maybe first 3 were increasing, and then after that, decreasing. Okay, so some of you are now going to come to a tutorial with me for this upstairs. So the tutorials, remember, look at look at both my material and Saeed's. I just want to say one last thing. So for my material in your tutorial this week, you'll be looking at questions 1, 2, and 3 on page 8, exercises 1.1. So exercises 1.1, questions 1, 2, and 3 will what we'll be looking at. Okay? Oh yeah, thank you. Cheers. Yeah.
I wasn't here when people were getting notes. I wasn't in the
Okay, yes, you'll need one of those. Yep. Okay.
Thank you.
If someone could bring the signature sheet down, please. Yeah, you didn't get these last time, no? There you go. Okay.